everyone. This video is the continuation of our last video on the three fundamental lemmas of calculus. Here we're going to discuss uniform continuity and use uniform continuity to prove that continuous functions are Riemann integrable over closed intervals of real numbers. We're not going to be completely rigorous, but focus on the role that uniform continuity plays. We leave out some technical details that we can fill in later. So uniform continuity says that for any epsilon greater than 0, there exists a delta greater than 0, such that if the distance from x to y is less than delta, that implies that the distance from f of x to f of y is less than epsilon. The important detail here is that uniform continuity is a much stronger condition than regular continuity. For regular continuity, we only need to find a delta corresponding to epsilon at a particular point A. Remember, it was x minus a is less than delta. But it may very well be a different delta for each value of a. Uniform continuity says that there's some value of delta such that every pair of x and y that are close enough together will keep f of x and f of y close together as well. So in calculus books, the integral is introduced as a definition, but not a theorem. If you haven't already, please watch the first two videos we did on calculus, the casual introduction to calculus and the proof of the fundamental theorem of calculus. But we defined an integral as the integral from a to b of f of x dx equals the limit as n approaches infinity of the sum from 1 to n of f of star x of I times delta x, where delta x equals b minus a over n, meaning that the interval here from a to b is divided up into n subintervals. And so the delta x is the length of one of those intervals. So there's n of these, and then delta x is the width of one. Then x star sub I is a sample point lying inside the interval from x sub I minus 1 to x sub I. So the calculus books introduce partitions, sums, and so on, and then say that if the sum of the rectangles approaches a limit as the partition approaches infinity, then the integral exists and the function is integrable. Then they skip over with a hand wave whether any functions are in fact integrable, that is, whether the integral exists at all. But there's a fascinating amount of machinery going on behind the scenes that introductory calculus books just gloss over, because getting a handle on which functions are in fact integrable is a very difficult question. And to get even a limited answer to that question requires uniform continuity. That's as far as freshman calculus goes. It presents a theorem without proof claiming that a large class of useful functions are indeed integrable, namely continuous functions over a closed interval of real numbers. The reason they restrict their claim in this way is that continuous functions over a closed interval are uniformly continuous, and we need that fact to prove integrability. The reason this theorem is left unproved in freshman calculus is that in order to use uniform continuity, we need to prove that continuous functions over closed intervals of real numbers are uniformly continuous, and proving that requires concepts from topology. A big question in real analysis is, can we expand this class of functions? Are there more functions that we can integrate than those that are continuous over a closed interval? That is what led mathematicians eventually to Lebesgue integrals, which we'll explore in the next video. So regarding this definition, these sums are called Riemann sums, and the integral defined this way is called a Riemann integral. They're named after the German mathematician Bernhard Riemann, who presented them in 1854. This definition was the first rigorous formulation of the integral of a function over an interval. So Riemann did not specify how we choose the sample point. It can be any sample point in here. Anything between here and here can be the sample point. So we can do it a few different ways. So we can just mechanically say that the sample point is going to be the left side of every interval. Oops, I need one more. Like that. So then if we choose the left point, then we would multiply the left point times the width of the interval. So it would be dx times this height. So it would be a rectangle like this. And then here it would be a rectangle like this, then a rectangle like this, and a rectangle like that. So then you add those up, and that's an approximation of the area under this curve. Or we can do it using the right side. You sum up the boxes, but now we're taking the height at the right side of each interval. Or we could do it a third way, And we could just take the midpoint of each one. Then the box would kind of probably go half in and half out of each interval. The right sum has a little advantage, which is that it simplifies to just f of xi times x. But the midpoint probably will give us a little better estimation because it's kind of halfway between the two, right? Then one more way of doing it would be, instead of taking the midpoint of the intervals, we could take the midpoint of the values of f. So we could go halfway between here and here. So the boxes would be like this. So this one would be the average of these two. So you add the two ends together and divide by 2. This one would be you add the two values in the range together and divide by 2. So then to get the area of the rectangle, you would just multiply this by the width of that rectangle, which would be x to the I minus x to the I minus 1. Do you recognize this formula? What if we say that b1 equals f to the x I minus 1, and b2 equals f to the xi, and h equals xi minus 1? If we rewrite this formula then, using these, we get 1/2 h b1 plus b2. That is the area of a trapezoid. This is one of those moments that makes math so cool, where something out of left field suddenly makes sense. At least it did to me. I know this formula, but I've never really gotten why we're adding together the bases and then taking half times the height. But now suddenly it makes perfect sense, because what we're really doing is taking so here we have, if we're taking the area of this, it's a trapezoid, right? From down here to up here. Or another way to think about it is we're taking the two bases, b1 and b2, taking the average of those two and multiplying it by the height. So what a trapezoid is, it's just the area of a rectangle where you average the two bases. So now it suddenly makes sense to me, and I'll never forget this formula. So anyway, because of this method of choosing the sample point is called the trapezoidal rule. So it's called the trapezoidal rule, but what we're really doing is taking the point that's halfway between the two values of f. Another way to take the sample points is to take the infimum of the value of f in each interval, or the supermum. So if we have this again, so in this interval, the supermum's here. In this interval, maybe it's a little bit higher here. In this interval, the supermum's maybe here and here. And then the infimum would be here, here, and then here the infimum is down here, and then here. So you're still just making rectangles. You're choosing them in a slightly different way. So you have one set of rectangles that's the infimum of each interval, and then one set that's the supermum of each interval. So we can label the supermum of f in each interval as capital M sub I, and the infimum of f in each interval as lowercase m I. So then we use those values as the sample points. So see, they're going to be in a different spot each time. Like here would be the sample point here. Sometimes it's over at the right. Sometimes it's at the left. Sometimes it's somewhere, in the middle somewhere. This method of taking the sum of the intervals of the partition is named after a French mathematician, Gaston Darbu, who had very cool glasses. He was born in 1842, so was only 12 when Riemann presented his definition of the integral. He's not as well known, but there are many concepts in mathematics named after him, including this particular method of handling integrals, which is actually the usual way freshman calculus books handle the Fundamental Theorem of Calculus, although most books don't mention him by name. So if we take the sum of the rectangles using the upper limits, we have the sum from I to n of capital M I times the width of the partition, right? So this is the maximum value inside one interval, and then this is the width of the interval. So again, we're just taking the area of that rectangle, summing them up. This is the upper sum, and then the lower sum is the same, where f is the function and then p is the particular partition. So this one is called the upper Darbu sum, and this one is called the lower Darbu sum. So if you remember our proof of the Fundamental Theorem of Calculus, these might look familiar because this is how we proved the Fundamental Theorem of Calculus, because we took the upper sum and the lower sum and then squeezed the value of the integral between those two values as the partition got finer and finer. And then these two values, the infimum of the upper sums and the supermum of the lower sums, so this is called the upper Darbu integral. And this is a little bit weird because the upper Darbu sum is the value when you add all of these rectangles together. but then we're taking the infimum for every partition of AB. So we're taking finer and finer partitions, and then as we take finer partitions, the sum is going to get closer and closer to the actual value of the integral. So there's some minimum number that's as close to this integral as we can get it. So that's why we're taking the infimum of all of the different upper sums of each partition. Okay, and then the lower Darbu integral is the same thing, but with the supremum of the lower sums instead of the infimum of the upper sums. So we can use these two values as an alternate definition of the integral. The Riemann definition says that a function is integrable when the limit of those sums exists as the number of subintervals approaches infinity. Using these upper and lower bounds, we can say that a function is integrable when the lower integral and the upper integral are equal. So if these two values are equal, then the common number is called the integral of f on AB. This integral is identical to the Riemann integral, meaning a function is Darbu integrable if and only if it is Riemann integrable. So there's a problem with these Darbu integrals. Did you pick up on what it was? We'll come back to that a little later. So anyway, those are several common ways of taking the sample point. The important point about the Riemann definition of an integral is that it defines the integral in terms of any sample point within the subinterval. Riemann did not specify what that point should be. But we still haven't discussed the question we started with, which is which functions are Riemann integrable. It is because of the way Riemann defined his integral as these vertical slices under a curve that in order to be Riemann integrable, the function must be uniformly continuous. So, as I stated previously, the most useful result for Riemann integrals is presented in freshman calculus books, which is that all continuous functions over a closed interval from a to b are integrable over that interval. Here's the Riemann definition of the integral again. So we need to show that this limit exists. So what does this mean using our epsilon delta definition? If you look closely here, the limiting variable is not the x, it's the n. So we need to show that for every epsilon greater than 0, there exists a number capital N such that for all n greater than capital N, the distance from f of x to L is less than epsilon. Right, so what we need to show that for every epsilon here, we can show that there's some point after which these sums are all going to be close to the value of the integral. Or to flip it around, for any epsilon greater than 0, there exists a delta equaling b minus a over n, such that if the partition is finer than delta, then the difference between the limit and the sum is less than epsilon. So in other words, if this is a and b, and then we divide it by n, there's some partition where if n is big enough, then then the slices are thin enough that this sum will be closer to the limit than epsilon. So the problem here is we're not just closing in on a particular value of f for a particular value of x. We're actually talking about the sum of many values of x approaching a certain value. So it's not enough that f be well behaved at a particular point. A single value of f going off in an uncontrolled way would mean that the limit can't exist. So in order to prove that this limit exists, we need to prove that all of f on the interval are well behaved. They're going to have to all be within a certain range. That's what uniform continuity gives us. This is why the theorem only applies to closed intervals of R, and why Riemann intervals give us trouble if the limits of integration are infinity. So topology will show us that any continuous function over a compact set is uniformly continuous, and that closed intervals of real numbers are compact. That's not necessarily true of a function over all of R or over an open set. So because of course, for example, y equals x squared, it goes up forever. You can't go out to infinity. You can't take the integral of that, right? But for a closed interval of R, we'll see that for any epsilon greater than 0, there exists a delta greater than 0 such that for any x and y in the interval, with x minus y less than delta, f of x minus f of y is less than epsilon. So with this fact, we can prove that the limit of the sum exists as the partitions get ever finer. So the trick is that for any epsilon you give me, instead of finding a delta that works with that epsilon, we're going to find a delta that works with that epsilon divided by 2 times b minus a. We can do this because the statement of uniform continuity is true for any epsilon. So whatever epsilon you give me, it must be true for one that is smaller as well. So since we know that f is uniformly continuous, we know that there exists a delta such that when x minus y is less than delta, that implies that f of x minus f of y is less than our epsilon, which we're using epsilon divided by 2 times b minus a. So then we just pick a partition such that x sub I minus x sub I minus 1 is less than delta. That is, that the slices are smaller than delta. So then, since m sub I is the supremum of f of x in the interval, and m, lowercase m sub I, is the infimum of f of x in the interval, we know that mi minus lowercase mi is less than or equal to epsilon divided by 2 times b minus a, and that, of course, is less than epsilon divided by b minus a. These little algebra tricks, you see them all the time in real analysis. They're clunky, and it doesn't matter. This number could be 10. You just know you want this number to be less than this number. So just pick anything, just divide it by something, and then you always know that it's going to be there. We've seen Rudin do that 100 times, so here it is again. So since this statement is true for every I, then the upper sum minus the lower sum equals so this just is the definition. This is the definition of upper sum, right? This is just the sum of the rectangles. So this is the width of the slice times the supremum of f of x in that slice for each one. So you just add all those together, that's the upper sum. And then this is the lower sum. This is the minimum, the infimum of f of x in the slice times the width of the slice gives you the area of the box inside the curve. So that's all that is. So it's just the bigger sum minus the smaller sum. And then we can just rewrite that. So this is just distribution. We just factored out the x minus x. So it's mi minus mi times xi minus xi minus 1. This is less than. So what is this? This is where we're using uniformly continuous, because here we know, because f is uniformly continuous, that any two values of f are going to be less than epsilon divided by 2 times b minus a. So that means because the interval is smaller than delta, the distance between these two in particular has to be less than our epsilon. And our epsilon is epsilon divided by 2 times b minus a, which is less than epsilon divided by b minus a. So this is less than this. And then this is just the sum of the widths of the partitions. So this expression equals, this equals the full distance from a to b. So this equals this. And that, cancel the b minus a, and you get epsilon. So look at that. Assuming the compactness of a closed interval of real numbers, which gives us that it's uniformly continuous, we just proved that continuous functions over that interval are Riemann integrable. So there are some steps that we left out here, because to do it rigorously, this proof relies on making finer and finer slices. So we have to prove that, in fact, if you make the slices finer, you're going to get a better approximation of the area under the curve. So we're skipping that part. You can kind of see it, but that's sort of a technical step. So the important thing here is that uniform continuity means that as the approximation gets closer, meaning that epsilon is getting smaller, every u minus L, meaning the upper sum minus the lower sum for any partition as they get thinner, will be less than that epsilon. So really, in order to prove that a continuous function f over a closed interval is integrable, we used the topological fact that a closed interval of real numbers is compact and hence is uniformly continuous. But, final thing, did you notice what's wrong with Darbu integrals? They assume there exists a maximum value and a minimum value in each of the intervals. That, in other words, is the extreme value theorem. And that also requires the fact that a closed interval of real numbers is compact. It's not the standard way of doing it, but it's actually possible to prove this integrability theorem without using uniform continuity. If you want, let me know and we can do it. But you still have to use the extreme value theorem. So even if you find a way around uniform continuity, you still need the extreme value theorem. Both uniform continuity and the extreme value theorem require compactness. So the bottom line is, since the extreme value theorem and uniform continuity are both results of compactness, it's really compactness that is the required property of real numbers. Compactness and connectedness are the two things we need from topology in order to move forward. Okay, that's it. Next week, we will look at Lebesgue theory, with which it becomes possible to integrate a far larger class of functions than merely those that are continuous over a closed interval. And then we will begin actually building the theory of topology. Thank you. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.